Hello! The fundamental equations describing aerodynamics are the Navier-Stokes equations. Scientists have been searching for a solution to this for a long time now. If you are able to solve the Navier-Stokes equations, you can earn a prize of $1 million. This award has been made available by the Clay Institute of Mathematics. In practical applications, the Navier-Stokes equations are solved numerically by computers. All of this is rather complex, and it is not the objective to let you become specialists in computational fluid dynamics. I'm interested in the application of aerodynamics to aircraft performance. I will demonstrate some fundamental principles, and in the end it turns out that we can accurately describe the complete aerodynamics of an aircraft in a single parabolic equation. So, let's get started. Aerodynamics is a combination of the word aero, representing the air through which the aircraft move, and dynamics, the dynamic motion of air. All aircraft are capable of flying at a constant altitude and speed for a prolonged period of time. In that situation, the aerodynamic lift and drag forces are balanced by the weight of the aircraft and the thrust of the propulsion system. In fact, there is only one resulting aerodynamic force acting on the aircraft as a result of the airflow around the aircraft. It is convenient to separate the resulting force into a component perpendicular to the direction of flight, lift, and one parallel to the direction of flight, drag. The wings are designed to generate lift with the least amount of drag. If we would take a cross-section of a wing, you would see it has a special shape. This is what we call an airfoil. The air flows over and underneath the airfoil. In this image, we freeze the motion of the airfoil and let the air flow around it. That is useful when making drawings. In real life, of course, the aircraft is moving and the air is standing still. The motion of the air around the airfoil results in pressure forces and friction forces. Hundreds of years back, the famous Dutchman Daniel Bernoulli discovered there is a relation between pressure, density and airspeed. He found that pressure plus a half times air density times velocity squared is constant along a streamline of the flow. This equation is valid in what is called incompressible flow. So a flow where the air density is constant. This is the case when the velocity is not too high. More on this condition of incompressibility will be treated later. There is one streamline that exactly ends on the nose of the airfoil. Over there, the end velocity is 0 and the pressure is the summation of P plus a half rho v squared. This is why we call P the static pressure. It is the pressure felt when there is no motion. The term half rho v squared is called dynamic pressure. At the same time, this equation reveals that since the flow accelerates over the airfoil, pressure reduces. The conservation of mass dictates that air must accelerate around the airfoil. Over here you see a typical pressure distribution. It may be interesting to note that this is in fact the large region of low pressure that generates lift. In fact, there is a suction force pulling the airfoil upwards. So how does an airfoil generate lift? One way of looking at it would be the pressure. Since air is accelerated over the wing, a low pressure region is generated. Due to the shape, this pressure is lower than at the bottom, and therefore a net upwards force is created. Perhaps a more natural way of looking at it is the following. The shape of the wing is such that it deflects the flow downwards. It must do so because otherwise a vacuum would be created. Newton's third law tells us that a change in momentum per second must equal an opposite force. Action is reaction. In other words, the wing pushes the air down and as a result an upward reaction force is created. In this figure you can see the change in momentum indicated. Note that m dot is the mass flow per second. For a constant velocity, m dot times v is the time rate of change of mass times velocity. F equals the change of m times v with time. You can also feel this yourself if you stick your hand out of the window of a car. When you place your hand under an angle and deflect the air, you generate a lift force. The larger the deflection, the larger the force. Now you have some understanding on how lift is created. Let's go back to the airfoil and investigate an important cause of drag. If you would zoom in on the airfoil, you would see there is a thin region of air with a low velocity. At the surface of the airfoil, the velocity of the air is zero because of friction. This thin region of viscous flow is called the boundary layer. It causes a shear stress or friction force. This contributes mainly to the aerodynamic drag. If the flow nicely follows the shape of the airfoil in a smooth manner, it is called laminar flow. It is not always possible for the flow to follow the curvature of the airfoil smoothly. Typically, there is a point where the streamlines break up and become quite irregular. From that point onwards, the flow is called turbulent. You can imagine this depends on the geometry of the airfoil and also the angle under which it is placed in the flow. The friction is much larger when the flow is turbulent. The angle between the airfoil and the oncoming air is called the angle of attack alpha. If this angle is small and the airfoil has the right shape, the flow will be almost completely laminar. At larger angles, it becomes difficult to follow the shape of the airfoil and then the flow will partly separate. At even larger angles of attack, the flow may be completely separated. This process can be nicely visualized in a wind tunnel experiment where particles are immersed in the fluid. In the past, people did many experiments like this. It was found that the aerodynamics depend on various important parameters. The geometry of the configuration, the angle of attack, the size of the object, the airspeed, the air density, and two more, the Mach number and the Reynolds number. These last two I will discuss later. Based on these observations, it is possible to derive an equation that describes lift. Lift of a wing is a coefficient CL multiplied with the dynamic pressure and the wing surface area. Remember that the force is a pressure times the surface area. A half times rho times v squared is the dynamic pressure of Bernoulli's equation, and S is the wing surface area. The lift coefficient represents the geometry and the angle of attack of the wing. This makes it possible to compare values of CL for different wings of different shape and size. If you would measure the lift of any aircraft for different angles of attack, it has this shape. There is an area of linear lift increase with angle of attack with a constant slope CL alpha. Normally, aircraft fly with a CL within this linear region. At a certain angle of attack, the flow starts to separate. Then we see a maximum lift at high angle of attack, beyond which the flow is completely separated. This is called stall. If an aircraft flies at different airspeeds, the pilot can adjust the lift by changing the angle of attack accordingly. So at low airspeeds, a high angle of attack is needed, whereas at high airspeeds, a small angle of attack is needed to achieve a force equilibrium. The force expressed in newtons will be completely different when the aircraft size is different. However, when the dimensionless lift coefficient is plotted, different wings and airfoils can be compared in a fair manner. The maximum lift coefficient is quite important in terms of aircraft performance. Summarizing, lift is a function of a coefficient CL, the dynamic pressure and the wing surface area. The lift coefficient is a dimensionless quantity that represents the geometry of the configuration. CL increases almost linearly with angle of attack up to the maximum lift coefficient beyond which flow separation occurs. How drag behaves is the topic of the next video.